Hello and welcome. I'm Matsaini bin Cotton. Now, last time we talked about scalars and vectors. Today, we're going to build on that with something that is absolutely critical for everything we do in mechanics, and that's the system of units. This stuff, it's literally the foundation of all engineering, so let's jump right in.
So I want you to imagine this for a second. You're the lead engineer. You've got a brand new satellite, and its specs are all in pounds. But the rocket that's supposed to carry it to orbit, that's spec'd out in kilograms. So what do? Do you just bolt them together and, hope for the best? No way, not a chance. A simple mistake like that isn't just a rounding error. It's how multi-million-dollar projects fail catastrophically. And that's exactly why understanding units is completely non-negotiable for us.
You see, the problem is actually pretty simple. For engineers all over the world to build things that work, things that are safe and reliable, we all need to be speaking the same language. And I'm not talking about English or Malay. I'm talking about a universal language of measurement. And that's precisely what a system of units gives us.
All right, so Section 1, Why Units Matter. And the subtitle here is really the key, the foundation of engineering safety.
So just think about it for a second. What actually happens if you try to add meters to millimeters in the same equation without converting first? Or what if you plug pounds into a formula that's expecting kilograms? What you get is, well, it's just chaos. Your numbers become completely meaningless, and the things you design, bridges, cars, airplanes, they could become dangerously unpredictable. So that brings us to the solution. How do we fix this? That's where we get to Section 2, the global standard, SI. This is all about creating that universal language for every engineer on the planet. And the solution is beautifully simple. The SI system, which stands for the International System of Units, it's basically our universal translator. It gives us one standard unit for every key physical quantity. Now, for us in mechanics, we really only need to focus on three fundamental ones to get started: length, time, and mass. These are what we call our base units.
Okay, so Section 3, the three base units. I like to call these the alphabet of engineering mechanics, because once you get these three down, you can build just about any other unit you're ever going to need.
So first up, we've got length, and its SI unit is the meter. Now, I know this sounds super basic, but trust me, it is absolutely fundamental. When you look at an engineering drawing with dimensions in millimeters, or you calculate the span of a bridge in meters, you're using this base unit to define the physical world around us.
All right, next up, mass. The base unit is the kilogram. Okay, pay close attention here because this is a big one. Mass is not the same thing as weight. Mass is a measure of how much stuff, how much matter is in an object, and that amount is constant whether you're on Earth or on the moon. Weight is the force of gravity on that mass. We'll get more into that later, but for now, just remember, mass is constant.
And rounding out our big three is time, measured in seconds. Now, here in statics, we're usually dealing with things in equilibrium, right? Things that aren't moving. But time is still a core concept, and it becomes absolutely essential once we get into dynamics, where we're analyzing motion, velocity, and acceleration. So, we have our alphabet: meters, kilograms, seconds. Now let's start building words. And the first and maybe most important word for us in statics is force. So, Section 4 is all about this derived unit, the Newton, and how we build the concept of force from our base units. So where does the unit for force actually come from? Well, it comes from maybe the most famous equation in all of physics, Newton's second law. Force equals mass times acceleration. This simple equation perfectly shows how we can combine our base units to create something new. And here it is, the official definition. The unit of force is called the Newton, which we write with a capital N. And 1 Newton is defined as the force needed to make a 1 kilogram mass accelerate at 1 meter per second squared. See how it's just a combination of our base units, kilogram, meter, and second? It's not magic, it's just mechanics.
Now, as engineers, we have to deal with some incredibly huge numbers and some incredibly tiny ones. Writing out all those zeros is just asking for a mistake. And that's where prefixes come in to save the day. They're our essential shorthand. So let's move on to Section 5, Scaling with Prefixes.
Okay, so what you're seeing here is the standard table of SI prefixes. For the big stuff, we're mostly going to use kilo for 1,000, mega for million, and giga for billion. For the small stuff, it's usually milli, micro, and nano. Honestly, you've just got to memorize these. They're that important. All right, let's put this into practice with a really common situation. You're working on a problem, you punch the numbers into your calculator, and it spits out an answer like this: 12,345.6 newtons. So the question is, how do we write this like a professional engineer?
Okay, so the process here is really simple. Don't overthink it. First, just look at the number. It's in the thousands, right? So the best prefix is kilo. To convert from newtons to kilonewtons, or kN, you just divide by 1,000. That's the same as just moving the decimal point 3 places to the left.
So that gives us 12.3456 kilonewtons. But hold on, we're not quite done. We also need to think about precision. It's a general rule in engineering that we present answers with 3 significant figures. Since our number, 12.3456, doesn't start with a 1, we round it to 3 figures. So our final, clean, professional answer is 12.3 kilonewtons.
But let's just pause here for a moment. What does 12.3 kilonewtons, what does that actually mean? Well, if we were analyzing a bridge, that number could represent the real physical load that a steel beam has to support. It's not just a number on a page. It's the real-world force that can make that bridge buckle or stand strong for 100 years.
All right, let's wrap this all up with our final section, number 6, your engineering rulebook. And I really want you to think of this as the mandate for professional practice. These are the non-negotiables.
So let's boil it all down to 4 simple rules you absolutely have to live by. Number 1, always use SI units in your calculations. 2, before you even start to solve, make sure every value is in a consistent unit. 3, a number without a unit is totally meaningless, so always state your units. And finally, number 4, use those prefixes to keep your answers clear, concise, and professional.
And I really want to leave you with this final thought. Mastering units isn't about getting the right answer on a test. It is a core tenet of engineering safety and our professional responsibility. When you eventually sign off on a design, you're staking your entire reputation on the accuracy of your work, and that accuracy begins with consistent units.
All right, excellent. We've now established our common ground, our shared language, the SI system of units. And with this powerful and essential tool under our belt, we are finally ready to dive into our next topic, the systematic methods for solving engineering problems. Thank you.